Guess it's time to get started. Welcome everybody. The sign sheet's making its way around. Please write your name on there. I think most of what we're going to talk about today is limits. That's certainly my plan, but if there are other things we need to see, we certainly are welcome to mention them. Let's go ahead and jump right in. So we're going to start with a graph, actually. So we're going to graph the piecewise function f of x equal to x squared plus 1 when x is less than or equal to 0, x plus 1 when x is greater than 0 and less than 3, and square root of x plus 1 when x is bigger than or equal to 3. So piece by piece, I like to go from left to right. So x squared plus 1, your usual upward opening parabola, shifted up 1, but only when x is less than or equal to 0. So it's going to be essentially the left side of that parabola. So here's the point 0, 1, and it looks vaguely like that. And then for y equal to x plus 1, that's a straight line with a slope of 1, also going through the point 0, 1. So I get the point 0, 1, 1, 2, 2, 3. And I would get the point 3, 4 if it was there, but it's going to be an open circle. It's going to look like that. And finally, the last piece, the square root of x plus 1, looks like your normal square root graph shifted 1 to the left, but we're not going to start over here because we're not starting until x is bigger than or equal to 3. So if we were to plug in 3, 3 plus 1 is 4, square root of 4 is 2. So we get the point 3, 2. And then it looks like your usual square root function starting there. It's kind of getting bigger as you go from left to right. It has kind of a curve to it. It's not particularly curvy there, but there is a curve there. And so the questions I really kind of want to explore here are what's happening at 1 and what's happening at 3. So I might ask a question like, what does f of x approach as x approaches 0 from the left side? Well, that's a lot of words to write to ask that question. You can just sit down there. A much more mathematical way of writing this question is, what is the limit as x approaches 0 from the left-hand side of my function f of x? A couple ways you can approach, you can approach this is either by looking at the graph, which certainly makes sense if you have a graph to look at. And so here, where's my red pen go? All right. So here, if x gets closer to 0 from the left side, or approaches 0 from the left side of 0, the corresponding function values get closer and closer and closer to the y value of 1. So what we would say here is that, right, pens. Yeah. The limit as x approaches 0 from the left of our function is 1. I want to talk a little bit about the language here. So I would say the limit is equal to 1. That does not mean that the function actually has to be equal to 1. All this statement means is that as x gets closer and closer to 0, but not equal to 0, the function gets closer and closer to 1. Maybe it's equal to 1 at 0, maybe it's undefined at 0. Talk more about that in a minute. What about the other side? What is the limit as x approaches 0 from the right-hand side of f of x? Well, again, looking at my graph here, I can see that as the x values get closer and closer to 0 from the right, the corresponding y values also get closer to 1. So we could say, I feel dumb writing the same thing twice, but I'm going to write it twice. The limit as x approaches 0 from the right of x is equal to positive 1. Another way you could think about this is that if x were to be a value really, really close to 1 from either side, we would get a y value really, really close. Sorry, if x was value really, really close to 0 from either side, y would be really, really close to 1. For example, if x were to be equal to 0.001, which is a little bit bigger than 0, I would plug that into the middle part of the function because that's where x is between 0 and 3. And so then f of 0.001 would just be 0.001 plus 1, or 1.001. So we can see it's really, really close to 1 if x is really, really close to 0. I'm going to say that a lot, might get kind of annoying, but the whole thing about limits is you're just asking, what's this y thing doing as x is getting really, really close to this particular value? I would also mention here that since the left-hand limit and the right-hand limit have the same value, we would say that the overall double-sided limit exists and is equal to that value. So notably, these two things together means that the limit as x approaches 0 of f of x is 1. I'm going to say that more generally here. We're still going to continue with this example, but I'm going to point that out. So we typically say that the limit as x approaches a of f of x is equal to L if and only if, again, normally I would abbreviate that with what? If the one side of the limits are both equal to that as well. So if both the limit as x approaches a from the left-hand side of f of x is equal to L, and the limit as x approaches a from the right-hand side of f of x is equal to L. Excuse me. On the other hand, if you look at what's going on at 3, well, let's actually look at what's going on at 3. So for x equal to 3, we're going to look at the limit as x approaches 3 from the left of f of x. And here's where that idea of closeness is going to be more important. Because we'll point out, well, so I'll just label this here. So this whole would be the point 3 comma 4, although it's not actually there. And so what's happening here is that as x is getting closer and closer and closer to 3 from the left, the y values are getting closer and closer and closer and closer to 4. So for example, and I'm going to say it's equal to 4 here. I'll just point out that f of, say, 2.999. Well, again, I'm just plugging that into the middle piece of the function. Since x is a little bit less than 3, I'm going to get 2.999 plus 1, which is 3.999. Really, really close to 4, but not equal to 4. That's fine. It doesn't have to equal 4. But we can get as close to 4 as we want. So more 9s, it's too close and close to 4. So like 2.999, you can get 3.999. And that does mean for us that this limit is equal to 4. On the other side, the limit as x approaches 3 from the right-hand side of f of x. Well, if we look at the right-hand side of 3, we see that as we approach 3 from the right, and I didn't label that point either. Sorry, bad labeling here, James. That the y values are getting closer and closer and closer to 2. So we say that the limit as x approaches 3 from the right of f of x is equal to 2. And what that means for us is the overall limit as x approaches 3 doesn't exist, because the left-hand limit and the right-hand limit aren't matching that. Well, sorry, you can't quite see that. Again, I'll point out, if you can't see something, well, you always, hey, James, can you move it up or move it down, just so you can make sure you can see all the things. So here we would say that the limit as x approaches 3 of f of x does not exist, which we usually abbreviate is dne. And the reason it doesn't exist is because, in this case, the limit from the left and the limit from the right don't match each other. So, some things to know about limits. I wasn't really showing my work here. Well, actually, no, we'll do another example. We don't need to sell that. Yeah, let's do that. Cool. So let's look at another one where we're not going to graph it. Another piecewise function. So let's say we have, example number 2. Here we have g of x equal to the following. X cubed plus 2x when x is less than 1. The cube root of x plus 5 when x is bigger than or equal to 1 and less than or equal to 8. And then lastly, x minus 1 when x is larger than 8. We're going to look now at, often when you're looking at piecewise functions, the places of interest are the places where you change from one piece to the next piece. So we're going to look at what's happening at x equal to 1 and x equal to 8. So let's go ahead and examine the limits from either side of 1. So the limit as x approaches 1 from the left, and we'll do the right-hand side in a second. So without the graph, I have to do a little bit more looking at what's going on. So if I'm approaching 1 from the left of this function, I'm using the piece of this function where x is less than 1. So I'm going to say, great, that's the limit as x approaches 1 from the left of x cubed plus 2x. And a good rule of thumb, although it's technically not always true, but most of the time, if you're trying to evaluate a limit, you can simply substitute in the value that x is approaching and see what you get. If you get a real number, you're almost always good to go. The exceptions are usually actually piecewise functions. So we'll see how that plays out later. If I plug in not 0.9 or 0.99 or 0.9999, if I plug in 1, because that's what we're approaching, we're going to get 1 cubed plus 2 times 1, which is 3. So as x approaches 1 from the left, the limit's 3. Let's see what's going on from the right-hand side. So if I approach 1 from the right-hand side of g of x, I feel like I'm saying that wrong. If I approach 1 from the right, oh, thank you, yes. But if I'm not looking up, because often I'm like this, say words, no problem. So if we take the limit as x approaches 1 from the right of g of x, we're on the right-hand side of 1. Now, technically, both of these pieces are on the right-hand side of 1. But we're not just on the right-hand side of 1, we're on the right-hand side of 1, and we're trying to get really, really close to 1. So it can't be this piece where we're beyond 8. It has to be this middle piece where x is getting really, really, really close to 1 on the right-hand side of 1. So we're going to use this piece of the function, cube root of x plus 5. I'm kind of ignoring those limit rules you might have talked about in class, and I'm just doing the easy thing, which is plugging in x equal to 1. And here I'm going to get the cube root of 1 plus 5, which is 1 plus 5, which is 6. And so we can say, based on both of these two things here, the limit as x approaches 1 of g of x does not exist. Left-hand side, right-hand side, not matching up. Let's look at the other side of things. My paper's in order here. So much going. All right. So if we look at approaching 8, well, let's see here. The limit as x approaches 8 from the left of g of x. Now we have to use the piece where x is less than 8, but it gets still getting close to 8. So we're still going to use this middle piece because that's where x is approaching 8 from the left side. And that's going to be the limit as x approaches 8 from the left of the cube root of x plus 5. I'm just going to plug it in. I'm going to get the cube root of 8 plus 5, which is 2 plus 5, which is 7. On the other side of things, we can probably already see that we're going to get 7 as well. Let's write it out. Limit as x approaches 8 from the right of g of x. Well, now that we're on the right side of 8, we have to use the piece of the function where x is larger than 8. So that's going to be where the function is equal to x minus 1. And then we sub in 8 for x, we get 8 minus 1, which is 7. So we can say, though, in this case, since they're matching up, the limit as x approaches 8 is equal to 7. I'll say one more thing here. If you'd like to see it, I should move it up though. What is the limit as x approaches 13 of g of x? Well, better question. Which piece of the function should I use? The top, middle, or bottom piece? The bottom. Because if x is approaching 13, that means I need to use the piece of the function where that's in the domain, essentially. And the domain where x is equal to 13 is where x is bigger than 8. So we're going to say, okay, great, that's the limit as x approaches 13 of x minus 1. And then just like we did before, substitute in 13 for x. We don't have to look at one-sided limits here, because both on the right side of 13 and on the left side of 13, the function is still equal to the piece x minus 1. So we can just use that piece for both sides without having to think about the one-sided limits. Questions so far? Yes, I'm going to make a blanket statement that is mostly true. Mostly true. Most limits you should try to evaluate before doing anything else by just substituting in the value that x is approaching and seeing if you get a real number. If you do, 99% of the time, that's going to be the right answer. 1% of the time, someone has made up a really ridiculous piecewise function, and it's not going to be the answer, such as life. But most of the time, piecewise other functions, I call them normal functions, like polynomials, rational functions, trig functions, exponential functions, logarithmic functions. Most of the time, you're trying to evaluate their limits. If you just plug in whenever x is approaching, the number you get, if you get a number, is your answer, is your limit value. For example, if I asked, what's the limit? I was trying to number things here. Sometimes I do a good job of numbering things. It usually falls apart. The limit as x approaches 2 of x squared plus 4x plus 7. There's nothing to worry about here. Certainly when I plug in 2, it's not going to be undefined in any weird way. So I'm just going to plug in 2 and get 4 plus 8 plus 7, which is equal to 19. I would also point out that for this function, the function evaluated at 2 is equal to 19, right? There isn't a difference between the limit value and the function value. That's not always going to be the case. There are plenty of functions where the function is actually completely undefined at the value x is approaching. For example, I don't love that example. I'll pick a different example. The limit as x approaches, sure, let's go that way, 2 of x squared plus x minus 6 over x minus 2. And so for a limit like this, you should at least think about what happens when you plug in 2 before you move on to doing something else. So if I plugged in 2, I would get 4 plus 2 minus 6 over 2 minus 2, which is 0 divided by 0, which is not necessarily equal to 1. Occasionally it happens to be 1, but it's what's called an indeterminate form. So 0 over 0 is an indeterminate form. It's also undefined, but specifically, it's this kind of undefined. And the indeterminate form means, well, what it really means is you have to do more work. That's what it really means. If you get an indeterminate form, it means you have to do something else. Now, what it means mathematically is it could be anything. You can get any possible real number if you have an indeterminate form, or it could end up not existing. That's a possibility as well. But what it really means for us is we do more. So in this case, we're going to rewrite this as, well, actually, I'm going to graph it before I rewrite it. So we're going to graph f of x equal to x squared plus x minus 6 divided by x minus 2, which I'll point out, this numerator does factor. Factors as x minus 2 times x plus 3 divided by x minus 2. We knew x minus 2 was going to be a factor, because when we plugged into the top, we got 0. That's the fundamental theorem of algebra. If you plug in a number to a polynomial and you get 0, x minus that number has to be a factor. True story. And then, as long as x isn't 2, this is equal to x plus 3. So graphically, here's what this looks like. It looks like the line y equals x plus 3, which has a y-intercept of 3 and x-intercept of -3. But at 2, it's completely undefined. Here's our function. F of x equal to x squared plus x minus 6 over x minus 2. We're missing one point. The point we would get if you could plug in 2 here. If you plugged in 2 there, you would get a y value of 5. We have a hole at the point 2 comma 5. You could do a little bit of what's what I'm looking for here. I don't know. We could examine this a bit more and see, well, look, as long as x isn't 2, our f of x value is going to be essentially x plus 3. For example, if x is 1, well, 1 minus 2 times 4 divided by 1 minus 2, the 1 minus 2s are going to cancel. Right? As long as x isn't 2, the x minus 2 divided by x minus 2 cancels out. And so we get 1 plus 3, which is 4. And if x was 1.9, those would still cancel. We'd get 4.9. If x is 1.999, we'd get 4.999. It sure looks like as x is getting closer and closer and closer to 2, the y values are getting closer and closer and closer to 5. It doesn't matter that x can't ever equal 2 here. Limits don't care what is happening at the value we're approaching. Whatever's happening at 2 literally does not matter at all here if we're talking about a limit. It definitely matters if we're talking about continuity and other stuff. If we're talking just about limits, we don't care that the fact that f of 2 is undefined. Doesn't matter. I know I'm kind of harping on this point, but it's because it's important. Limits do not care at all what is happening at the value you're approaching. They care what's happening immediately next to it. On the other side as well, right? If x was like 3, my y value would be 6, or 3.1, sorry, not 3.1, 2.1, we get 5.1, 2.0001, we get 5.0001. So it sure looks like, oh yeah, the limit is going to be equal to 5. And it is. It's correct to say that the limit as x approaches 2 of x squared plus x minus 6 over x minus 2. Here's why it's so important. The limit isn't concerned with what's actually happening right at 2. Because if we're not able to plug in 2 because we're not concerned with what's happening at 2, then as far as this is concerned, this is exactly equal to this. As long as x isn't 2, x squared plus x minus 6 over x minus 2 is the same as x plus 3, as long as x isn't equal to 2. So as far as these limits are concerned, they're exactly the same, whether it's this more complicated expression or this less complicated expression. And then we're going to take a page from our older book and say, oh, wait, if you've got something easy like this, we're just going to substitute in the value that x is approaching and say, well, if x is getting really, really, really close to 2, then x plus 3 is getting really, really close to 2 plus 3, which is 5. A lot of the limits we're going to encounter are what we often refer to as the 0 over 0 types of limits, or indeterminate forms. There are other indeterminate forms as well. For now, we're mostly going to stick with 0 over 0 types because that's what we see a lot of, especially leading up to the definition of the derivative. So let's practice some of those. Let's see, what else have I got on? Yeah, okay. So I got lots of examples. Let me give you some here. And then we'll circle back around and talk about some of these limit rules. So let's say we have the limit as x approaches -3 of x squared plus 9 over, sure, x squared minus x minus 6. So it's always good to check to see what's happening here. Because sometimes people try to write things that look like they're going to require more work than they're actually going to require. So what should we do first? Factor is what I would do second. What'd you say? Plug it in. Always. Even if it might look like you're going to get 0 over 0, just check. So if I plug in -3 squared plus 9 over -3 squared minus -3 minus 6 is going to give me, let's see, 9 plus 9 is 18 over 9 plus 3 minus 6. I'm getting 18 divided by 12. 12, no, 6, apologies. 12 minus 6, which is going to be 3. No need to do anything else. So don't fool yourself into thinking you need to factor until after you've, well, no, don't factor until after you've at least checked to make sure you're getting 0 over 0. Let's look at an example where we are going to have to do this. Let's say the limit x approaches 2 of 4x squared minus 3x minus 10 over 6x squared minus 12x. And yes, we should check. We're going to plug in 2 and see what we get. Let's see, 4 times 4 is 16, minus 6, minus 10, yep, that's 0 on top. Let's see, 6 times 4 is 24, minus 24. Yep, definitely a 0 over 0 type. Okay, so we're going to rewrite it. Limit is x approaches 2. What I said before still holds. If you plug in a number to a polynomial, which the numerator and denominator are both polynomials, right? Just positive integer powers of x with nice coefficients. You plug in 2 to either one of those and you get 0, that means that x minus 2 had to be a factor. In the denominator, we can do a bit more. I can see in the denominator that I can factor out of 6x. I'm left with x minus 2. In the numerator, I'm not 100% sure how to factor that, but I can use that knowledge that x minus 2 has to be a factor. So if x minus 2 has to be a factor, then it's easy to reconstitute the rest of this quadratic. X times 4x will give me the 4x squared first term, and -2 times positive 5 will give me the -10 last term. And if I check the middle terms, they will come out to give me a -3x, because -2 times 4x is -8x, and x times 5 is 5x, and -8x plus 5x is -3x. So you can use that to your advantage if you're trying to factor a quadratic like this, and you know that x minus the number you plugged in is a factor. It's really, really straightforward to figure out the other pieces of the other factor. Then we get to do the nice thing and cancel the x minus 2's. So we have the limit as x approaches 2 of 4x plus 5 over 6x. And then since we don't get 0 over 0 when we plug things in, we plug in 2, and we get 4 times 2 plus 5 over 6 times 2, which is 13 over 12. So typically, when I see a limit that's a 0 over 0 type, one of the things I look for is to see if just can I factor some stuff. Let's do one more example here. Let's do, oh, where'd you go? Sorry, I lost my example. There it is. Let's try the limit as x approaches, let's do that. Let's do -3 over, sorry, of 2x squared plus 5x minus 3 over x cubed plus 27. And we're not going to write it out. We're just going to check mentally. If we plug in -3, we get 9 times 2, which is 18, plus -15 minus 3. Yeah, 18 minus 15 minus 3 is 0. And the denominator, -3 cubed is -27 plus 27 is also 0. So we definitely do get a 0 over 0. Which means that both the numerator and the denominator should be able to be factored because they are polynomials. I should stop for a second here. I keep saying polynomials. I should point out this expression without the limit, that's a rational function, right? It's a polynomial divided by another polynomial. And what makes these polynomials is that your variable x is only raised to non-negative integer powers. The coefficients don't have to be integers. They usually are, but they could actually be any, I guess any real number technically, although usually rational numbers are what we limit ourselves to. So that means here, I should be able to factor out an x minus minus 3 from the top and from the bottom, or x plus 3, as I should probably actually write it. So let's write this as the limit as x approaches -3 Okay, on top, I'm gonna have an x plus 3. And then the other piece, well, I need to have a 2x. I need to have a minus 1. Let's check to see if that works out. 2x times 3 is 6x. Minus 1 times x is minus x. And 6x minus x gives me the 5x middle term. Cool. The other one here is a little bit different. So I'm going to have an x plus 3 and then something quadratic. You may or may not have seen before how to factor a sum or difference of cubes. Here's how you do it. So here's the general formula. Right over here. A cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared. And for the sum of cubes, a cubed plus b cubed is equal to a plus b times a squared minus a times b plus b squared. There's an acronym for this called SOAP. SOAP. So if you look at a cubed minus b cubed, it's always the a plus or minus b, a squared plus or minus ab plus b squared. And the sign, so it's always a and b here, a squared, ab, b squared here. And the signs correspond to, well, if it's a minus here, then this is the same sign, opposite sign, always positive. And if it's a cubed plus b cubed, it's the same sign, opposite sign, always positive. That's something people like. So over here, this x cubed plus 3 cubed is going to factor as x plus 3 is the first part, and then we're going to have x squared minus 3 times x plus 3 squared. And it totally works. We cancel the like terms. I'm a fan of writing it out again, but I probably like to write too much. So the limit as x approaches -3 of 2x minus 1 over x squared minus 3x plus 9. And we plug in -3, excuse me, and we get -6 minus 1 over 9 plus 9 plus 9, which is -7 over 27. I wouldn't say so much the point, but the way we usually typically deal with them, yes, is to kind of make the piece of it that's giving us a 0 in the numerator and the denominator go away. But sometimes there's more to it than just factoring. For example, you might have to deal with something like the limit as x approaches 5 of 3 minus the square root of x plus 4 over x minus 5. Now, if you plug in 5, we are still going to get 0 divided by 0. We're going to get 3 minus the square root of 9 over 5 minus 5, which certainly is 0 over 0. And it really doesn't look like this factors at all, right? First of all, I'll say it's not a rational function, even though it is a quotient. But it's not a rational function because the numerator isn't a polynomial, right? You have a square root, which is definitely not an integer power of x. It's a fractional power of x. Typically, when we see square roots, there is a method for dealing with it, and the method involves multiplying the whole expression by the conjugate of the thing that has the root. So we're going to rewrite this in the following way. We're going to use the conjugate. So the limit as x approaches 5 of 3 minus the square root of x plus 4 divided by x minus 5. Well, the only thing we're really allowed to multiply by is 1, because we don't want to change the value at all. So when we multiply by the conjugate here, we're going to multiply by the conjugate of the thing that has the radical. So it's going to be 3 plus the square root of x plus 4. But then to not change the value of anything, we have to also multiply the denominator by that. So we're really multiplying by 1. A good rule of thumb here is that whenever you're multiplying a quotient by the conjugate of one piece, you actually want to multiply out the things that are conjugates, and you don't want to multiply out the things that aren't conjugates. By the way, I keep using the word conjugate here. When I talk about the conjugate of something, it's just the same expression, but the middle sign is the opposite of what it was. So terminology, the conjugate of A minus B is A plus B, and vice versa. Or you could just say A minus B and A plus B are conjugates. And the nice thing about conjugates is when you multiply them together, the middle terms add up to 0. So we multiply this out, A times A is A squared, A times B is AB, negative B times A is minus AB, and minus B times B is minus B squared. A times B minus A times B is 0. So we end up getting A squared minus B squared. Or as I would always phrase it, the first thing squared minus the second thing squared. The order definitely does matter here. So I want to point out that when you factor A squared minus B squared, you do get A minus B times A plus B. If you were to factor B squared minus A squared, the order switches and you get B minus A times B plus A. Close to the same, not exactly the same. So definitely make sure when you factor a difference of squares, it is always the first thing minus the second thing times the first thing plus the second thing. Back to here, we're going to multiply out the conjugates. So usually you should skip this step of actually multiplying out the conjugate things, meaning I don't really want you to write 3 squared plus 3 times the square root of x plus 4 minus 3 times the square root of x plus 4 minus the square root of x plus 4 times the square root of x plus 4, or square root of x plus 4 squared. Because we know that the middle terms are going to add up to 0. So whenever you multiply conjugates together, you should skip the step of writing out the conjugates and say, oh yeah, those go away. And you really just get still the limit, as x approaches 5, of 3 squared, which is 9, minus the square root of x plus 4 squared. And whenever you square a square root, you just get the stuff inside. Then be careful here. I'm going to make a mistake. Made a mistake. Because I have to be subtracting all of this, meaning it should be minus all that, and the minus sign has to distribute to all the terms that are in there. I'll point out again, in the denominator, you really, really, really don't want to multiply that out, because our goal typically is to make the thing that's causing us to have 0 in the denominator get canceled. We would love for this x minus 5 term to cancel. Foiling out this bottom part is not going to help us do that. So whichever things are conjugates, you should multiply out. The other pieces you should not multiply out. It's not going to help us get there. Let's see here. So I've got x minus 5 times 3 plus the square root of x plus 4. Simplifying the numerator. I should point out, we do have to write the limit every time, because the limit is asking a question. It's asking, what y value is this function getting closer and closer to as x gets closer to 5? If you don't write the limit, you're just saying, here's a function. You're not asking a question about it at all. So make sure when you're finding limits, you have to keep writing the limit until you no longer are writing the variable x, or whatever your variable happens to be. So limit as x approaches 5 of 9 minus x minus 4 is going to be 9 minus 4 is 5. That's going to be 5 minus x. X minus 5 times 3 plus the square root of x plus 4. Those things almost look like they cancel, but they're not quite the same. Let me ask you all a question. It's going to be an easy question. What's 7 minus 3? Everybody. Cool. What's 3 minus 7? Everybody. -4. What's 4 divided by -4? -1. Does it matter which numbers I pick? If I said it was 1,000 minus 3 and 3 minus 1,000, and I divide them by each other, would I still get -1? I would. So another way to say that is whenever you change the order of subtraction, you get the opposite sign thing. 5 minus x is the negative of x minus 5. We could even factor out the -1 if that's easier. I just don't often like doing that work because I'm usually in a rush. But it is true that 5 minus x divided by x minus 5 is going to be -1 as long as x isn't 5, which it isn't because it's the limit as x approaches 5 and we never get to 5. Cool. But if you want to show more work here, you can say I'm going to factor out the negative one either from the 5 minus x or from the x minus 5. Take your pick. I'm going to pick the 5 minus x. So if I factor out the negative 1, I'm left with a negative 5 plus x over x minus 5 times 3 plus the square root of x plus 4. And it is true that negative 5 plus x is the same as x minus 5. If we really wanted to, we could rewrite it to make it look nicer before we cancel things. And say you have negative 1 times x minus 5 over x minus 5 times 3 plus the square root of x plus 4. I don't think we need to do that, though. What we do get to say is x minus 5 divided by x minus 5 is 1. So then we're left with the limit as x approaches 5 of negative 1 over 3 plus the square root of x plus 4. And now in this next step, I'm going to plug in 5 for x and get negative 1 over 3 plus the square root of 5 plus 4. And since I no longer have any x's in my expression, I should not write the limit anymore. I've taken the limit. I found it. I'm going to simplify my answer and get negative 1 over 6. Sorry. Okay. Let's do some more. Limits, there's lots of limits. Limits kind of go on and on and on. Yeah, question.
Can you show like another example of a piecewise function?
Yes. The problem is the piecewise. So the piecewise limits are something kind of. They're the one really kind of we have to look at them with kind of an eye towards. What am I trying to say? It's kind of a different thing. And I'm not saying this very well at all. But the piecewise limits, well, like for example. Sure, we'll do that. So let's say I have a piecewise function. Let's say we have, sure, let's do that. Let's do x squared minus 4 or x minus 2 when x is less than 2. And sure, the square root of 5x minus 1 when x is bigger than or equal to 2. So there's a piecewise function, and I want to know if the limit as x approaches 2 exists, and what would it be? So often with piecewise functions, we have to deal with them in sort of a two-sided way. So if I want to know what is the limit, if it exists, of f of x as x approaches 2. Well, let's look at the one-sided limits. So let's look at the right side first. So limit as x approaches 2 from the right, I'm going to have to use the piece of the function where x is larger than 2. So that's going to be this square root piece right here. So I'm going to do the square root of 5x minus 1. This is a nice situation where we just get to sub in what x is going towards. We get the square root of 5 times 2 minus 1, which is the square root of 10 minus 1, square root of 9, which is 3. Great. Let's look at the other side. Look at the limit as x approaches 2 from the left-hand side of x squared minus 4 over x minus 2. We can't just plug in x equal to 2, because if we do, we're going to get 0 divided by 0. So in this case, we have to use some technique. Factoring and canceling, multiplying by a conjugate. Something else here, we can just factor and cancel. So here, we have the limit as x approaches 2 from the left. The numerator factors as x minus 2 times x plus 2. The denominator is just x minus 2. X minus 2 divided by x minus 2 is 1. So we're left with the limit as x approaches 2 from the left of 1 times x plus 2. And if we plug in 2 for x, we get 2 plus 2, which is 4. The left-hand limit is 4. The right-hand limit is 3. They're not the same, so the overall limit doesn't exist. So the limit as x approaches 2 of f of x in this particular example does not exist. Most of the time, though, I'll say you're gonna see piecewise functions mostly when we talk about continuity. That is usually the place where we use them to illustrate functions that are either discontinuous at a particular point or continuous at a particular point. They're not the only thing we use, but they're a majority of what we use for talking about continuity. Let's look at another thing here. I've got kind of one more example before I want to make a kind of summary of some techniques here. So let's look at, sorry, it's number 10. The limit as x approaches, sure, 3 of 6 over x minus 2 over x minus 3. And you can probably look at this and already see it's going to be a 0 over 0 type. The 6 divided by 3 is 2, and 2 minus 2 is 0. And 3 minus 3 is also 0. So definitely a 0 over 0 type. In this case, what we typically want to do, again, there's not really any factoring to do here yet. And I should say most of these examples are usually like a first step, and then there's after the first step, then there's some factoring to do. Here, we're going to get a common denominator. So in the numerator, we have a fraction, 6 over x. So we want to be able to put those two pieces together, 6 over x minus 2. So I'm going to rewrite this as the limit as x approaches 3 of 6 over x minus 2 over 1 times x over x, still divided by x minus 3. Simplifying the numerator here, we're going to get the limit as x approaches 3 of 6 minus 2x over x, all over x minus 3. I do not love fractions and fractions. So I would rather not have that. So instead of having 6 minus 2x divided by x, all divided by x minus 3, we're going to rewrite this as the limit as x approaches 3 of 6 minus 2x over x. Instead of dividing by x minus 3, we're going to multiply by the reciprocal, 1 over x minus 3. If you don't love that, I'll remind you that this denominator really is x minus 3 divided by 1. So we're really flipping and multiplying. Sometimes people accidentally get this kind of funky in their heads and they write it as times x minus 3 instead of times 1 over x minus 3. So be extra careful there. We're going to do a little bit more factoring here. We're going to write this as the limit as x approaches 3. We're going to write it as one fraction. I'm trying to cancel that x minus 3. I should not distribute the x in the denominator. I should not write the denominator as x squared times x, as x squared minus 3x. I should write it as x times x minus 3. So I want that x minus 3 to cancel out. In the numerator, I should factor out a negative 2. So I'm left with a negative 3 plus x. Negative 3 plus x is the same as x minus 3. So negative 3 plus x divided by x minus 3 is just 1. So now we have the limit as x approaches 3 of negative 2 over x. Plug in the 3, and you get negative 2/3. So here's what I would say about the things we've done so far. We often refer to these as kind of the algebraic techniques for dealing with the 0 over 0 limit. So limits. What do we do? The first thing you should do for the limit as x approaches a of some function, f of x is, one more time. Thank you, plug it in. So plug it in. And if you get a real number, stop. Probably your answer. Very, very, very rarely there's funky stuff going on with piecewise functions where it isn't. Okay, but what if you don't? Like, what if you plug it in? We plugged in and got 0 over 0. What that means for us is we have to do more work. And in my opinion, there's a few kinds of quote unquote more work. So I usually like to say, do some algebra. You can either factor and cancel. And almost always you're probably going to end up factoring and canceling at some point. You might have to multiply by a conjugate first. Conjugate if like there's a square root. Or you might need to get a common denominator if you have some fractions. Fractions in fractions, I should say. Those are typically the algebraic things we see that we need to do to deal with the 0/0 types of things. Now, I should say this list is not comprehensive. There's certainly other techniques for dealing with other types of 0/0 limits. For example, I'll point out the third thing here. Sometimes there's some trigonometry, some trig weirdness is probably the easiest way to describe this. Slash trigonometric identities might be a better way to describe kind of how to deal with the next limit I'm going to mention. So let's say that one's down here. Let's say we have the following limit. This list, I'm going to add to this list later on of some other types of things we're going to see that aren't just 0/0, but it's kind of a starting point. What if we had the limit as x approaches pi over 2 of 1 minus sine of x divided by cosine of x? All right, let's see what we get if we plug it in. It's always good to check, right? It's often, especially in class, a really good bet that the limit's going to be a 0/0. Still good to check. So we plug it in, we get 1 minus sine of pi over 2 divided by cosine of pi over 2. Sine of pi over 2 is equal to 1. Cosine of pi over 2 is equal to 0. So it is 0 divided by 0. And there's not an easy way to say this other than saying all the words. When you see 1 minus sine or 1 plus sine, or 1 minus cosine, or 1 plus cosine. Those four things, usually the right thing to do is to multiply by the conjugate of that. So the conjugate's in play here as well. So if we multiply by the I was going to number this. I think it's number 11 here. Yeah. Sorry, I like to try to number things so people can see them later. Yes, 11. Cool. All right. Yeah. So I'm going to write this as the limit as x approaches pi over 2 times 1 minus sine x over cosine x, and then we're going to multiply the top and bottom by the conjugate of 1 minus sine, which is 1 plus sine of x over 1 plus sine of x. Just like before, we don't multiply out the things that aren't conjugates. So in the denominator, we're just going to have cosine x times 1 plus sine of x in parentheses. In the numerator, we're going to actually multiply it out. And again, remember, the middle terms end up adding up to 0. So we're going to get 1 squared. We would get a plus sign and a minus sign, but those are going to add to 0. And then we get a minus sign times a sign, which is going to be minus sine of x times sine of x. Or as I would probably write it, as I would have written it. Limit as x approaches pi over 2 of 1 minus sine squared x all over cosine x times 1 plus sine x. And since we haven't canceled anything yet, it doesn't really make sense to try plugging in again, right? You typically don't want to try plugging in what x is approaching until you've done kind of something to get rid of some stuff. So this is where we're going to use a trig identity. 1 minus sine squared x is equal to cosine squared x. So we're going to write this as the limit as x approaches pi over 2 of cosine squared x divided by cosine x times 1 plus sine x. Reminder to everyone of my most famous trig identity, of the most famous trig identity. Sine squared x plus cosine squared x equals 1. Or in this case, 1 minus sine squared x is equal to cosine squared x. And now, cosine squared x divided by cosine x, one of those cosines cancels and we just get a cosine x on top and no cosines on the bottom. So we can rewrite this as the limit as x approaches pi over 2 of cosine of x divided by 1 plus sine of x. And now if we plug in pi over 2, we get a real answer. We get cosine of pi over 2 divided by 1 plus sine of pi over 2. Cosine of pi over 2 is still 0. Sine of pi over 2 is still 1. And 0 divided by 2 is, or 0 divided by any non-zero number is 0. Some other kind of interesting examples here. One of my favorites. The limit as x approaches 5 of the absolute value of x minus 5 divided by x minus 5. And what do I want to say here? So what I really want to say here is you can't just drop an absolute value. Like it doesn't just go away because we want it to, even though it would be great if it went away, because I do want it to. What we really need to know is that absolute value functions are really piecewise functions in disguise. I'll say that again. Absolute value functions are piecewise functions. We've just come up with a really convenient notation for them. So what I'll say here is a reminder, the absolute value of some stuff. If the stuff is already positive, great, you just get that. But if your stuff happens to be negative, then the absolute value of that stuff isn't just the stuff, right? We don't want to get a negative number out. The way we turn a negative number into the same corresponding positive number is by multiplying it by -1. So the absolute value of some stuff is equal to -1 times that stuff if that stuff was already negative, so that the -1 multiplied by it turns it into a positive. My favorite example is the absolute value of 5 is just 5, whereas the absolute value of -5 is -1 times -5, which is 5. So here's the piecewise function that the absolute value function is masquerading as. It's just x if x is already positive, and it's -x if x is already negative. And then you can put the equals to part it wherever you want. And graphically, you probably have seen this before. If x is greater than or equal to 0, which is over here, I get y equal to x. If x is less than 0, which is over here, I get y equal to -x. And there's the absolute value function I imagine most of you have already seen, right? Your typical V-shaped function. Cool. All that to say, we can do something, we can do something similar with this. So it's the case that the absolute value of x minus 5 is equal to, well, it's equal to just the inside stuff if that inside stuff is already positive. Which we could translate to be to saying that means x is bigger than 5. On the other hand, if the inside stuff happens to start off being negative, then the absolute value of that negative number is -1 times that negative number. So to deal with this limit, and this is very true for absolute value things in general, you often have to do the two-sided limits. We're going to look at the limit as x approaches 5 from the right, and the limit as x approaches 5 from the left, and see what happens. So the limit as x approaches 5 from the right, where x is bigger than 5, well, that means that the insides of the absolute value of x minus 5 are already positive, because x is bigger than 5, and the number bigger than 5 minus 5 is positive. So we can just simply write this as limit as x approaches 5 from the right of x minus 5 divided by x minus 5. Since x isn't 5, x minus 5 divided by x minus 5 is just 1. With the limit as x approaches 5 from the right of just 1. And here's one of those limit rules that I keep saying I'm going to talk about. The limit of a constant, no matter what x is approaching, if your function's a constant function, it's always 1. Doesn't matter where x is, the limit's still going to be 1, or whatever the constant value is. I'll say it again. The limit of a constant is always that constant, no matter what x is approaching. It could be 5, could be a billion, could be negative 13, doesn't matter. That being constant means your limit is the constant. On the other side of things, on the other side of 5, the limit as x approaches 5 from the left of the absolute value of x minus 5 divided by x minus 5. Well, now we have to replace the absolute value of x minus 5 with not x minus 5, unfortunately, but negative 1 times x minus 5. Because if x is less than 5, then x minus 5 is negative, and we want to get a positive output for the absolute value. So we get negative 1 times x minus 5 divided by x minus 5. Again, the x minus 5s do cancel, but now we're left with the limit as x approaches 5 from the left of negative 1 times 1. And again, the limit of a constant is just that constant. So we see that the right-hand limit is positive 1. The left-hand limit is negative 1. They're not the same. So the overall limit doesn't exist. So this limit does not exist. Graphically, here's how this function looks. It's not very interesting. It's undefined at 5. And to the right of 5, it's equal to positive 1. Always. To the left of 5, it's equal to negative 1. Always. Kind of boring, but some functions are boring. Let's see. Let me look here real quick. Sure, that seems good. Oh, we're talking about that. Okay. So let's briefly mention these. These limit rules are kind of a pain in the butt, to be perfectly honest. So here's what I'll say about these limit laws. We use them all the time, and we never use them. Meaning we use them all the time, but we never actually, unless specifically in your homework, like which homework assignment is this? No's homework assignment, where there's like compute the limits, state where you're using the limit law, each item is located. So most of the time we don't say we're using these limit rules, but you could. So how many? Yeah, sure. I don't really want to write them down. I will talk about them for a second. So here's what they say in regular words. The limit of the sum is the sum of the limits. Or as I wouldn't actually write that like that personally. I'm gonna write these down as I say them, and then I'll move the screen so you can see it in a second. But here's how I would write this. I would say that the limit as x approaches c of f of x plus g of x is equal to the limit as x approaches c of f of x plus the limit as x approaches c of g of x. And it could be a sum or it could be a difference. So let me show you what I mean here, and I'll kind of go back and forth between these screens here. Or maybe I could do something. Let's see how smooth I can be here. Not that smooth. Too bad. Let's see. Maybe. Okay, sure. Yeah, we got that. So there's the first and second rule. The sum and difference rule. The limit of a sum or difference is just the sum or difference of the limits, provided they both exist. So all these limit laws, you're assuming that both the limit as x approaches c of f of x and the limit as x approaches c of g of x exist. And I believe in this side they've said that they're equal to L and M or something like that. Okay, the next rule, the constant multiple rule. I guess it's rule 3 technically. So this is 1 and 2. So the constant multiple rule, And actually, what I would say about this first rule here up here is I would say the limit distributes across addition and subtraction. That's what I'm thinking about. This limit's getting applied to both of those here. Constant multiple rule, kind of a similar-ish idea. The limit as x approaches c of some constant times your function is the constant times the limit. Okay, we have a product and a quotient rule. Product rule, not surprisingly, says the limit of f times g is the limit of f times the limit of g. Or if you take the limit as x approaches c of a product of two functions, it's equal to the limit as x approaches c of f of x times the limit as x approaches c of g of x. Or as your book writes it, L times M. I think this is more illustrative personally. The quotient rule works with one kind of addendum. The limit as x approaches c of f of x divided by g of x is equal to the limit as x approaches c of f of x divided by the limit as x approaches c of g of x, as long as what isn't happening. As long as the limit as x approaches c of g of x is not equal to, we don't want to divide this. Couple more rules here. They're pretty not terrible. We have the power rule, which actually I don't remember. I think I know what it says, but let's check. I believe it says. See, the power rule says, yes, if you have the limit of a function to a power, you get the limit to that power. Cool, and the root, yes. Exactly what I thought. Okay, great. So power rule says you have the limit as x approaches c of f of x raised to some power. It's the same as if you did the limit of the inside part first and then raise that result to that power. And finally, the one I just looked at and don't remember what it was at all. I have a vague idea of what it was, but not exactly. Oh, I think it's the root rule. Yeah. Really, which is still the same, to be honest. The root rule just says if your power is a root instead, like 1 over n, same kind of idea applies. The limit is x approaches c of f of x, so the 1 over n is the same as if you did the limit of the argument first and then took the nth root of it or raised it to the 1 over n power. I will point out, you do have to be a little bit careful here. If n is even, the insides here do have to be approaching a non-negative number. So you can't take an even root of a negative number. Okay. All right, so there's all these terrible limit laws that we almost, except usually with the exception of one homework assignment, never really talk about or refer to at all. But let me point out kind of, I feel like, let me actually look at one more thing here real quick with the, we only have 11 minutes left. I feel like there's one other thing I wanted to see. Yeah, okay, sure. Yes, okay, that's what I thought. So there's also some other rules that apply. They're not too terrible. Here they are. The limit as x approaches a of a I've changed my lettering completely here. Sorry, let's do x approaches c of a constant k. We already kind of talked about this. The limit of a constant is always going to be the constant. And then the limit as x approaches c of just x. Well, literally you're saying, as x is really, really close to c, what is x getting close to? C. And then we can kind of apply all these rules. We want to get a few more things like the limit as x approaches c of x to some power is just going to be c to that power. Kind of combining both this rule and this power rule here. So one could ask the question, one could have papers all over the place too. One could ask the question, one. Like, I'm not the one asking the question. I'm gonna ask the question. What's the limit as x approaches 3 of 4x squared plus 2x minus 5 over 7x plus 9? And cite all the limit laws you have to use. So I'll point out the way you should do this problem, if you're not asked to do it in this terrible way, is you just plug in 3, right? The actual way we would do this is be, okay, plug in 3, 4 times 3 squared plus 2 times 3 minus 5 over 7 times 3 plus 9 is something terrible. Let's see, it's 36 plus 6 is 42 minus 5 is 37 over 21 plus 9 is 30. That is how you should always do this problem unless someone specifically says to do it this long or terrible way. So here's what we're actually going to do though. So if we're going to citing all the limit laws, I might not be able to fit it on this piece of paper, but we'll see. So we'll start here. The limit as x approaches 3 of 4x squared plus 2x minus 5 over 7x plus 9. I'm first going to use the quotient rule and say, okay, the limit of a quotient is the quotient of the limits, meaning it's the limit of the top thing divided by the limit of the bottom thing. Now I'm going to use the sum and difference rule in each of the top and bottom. So in top, I'm going to say, great, the limit as x approaches 3 of 4x squared plus 2x minus 5. And I guess if I really wanted to be, okay, I should say, so here we're using the quotient rule. I don't love, by the way, I know it's a personal rant here for just a second. I don't love that we have like 3 different things called the quotient rule. There's the quotient rule for limits. There's the quotient rule for logarithms, where you type how like the log of x divided by y is the log of x minus the log of y. And then there's the actual quotient rule for derivatives, which is the thing we usually call the quotient rule. So I apologize that mathematicians aren't original and use the same name for everything, but this is not the real quotient rule. This is the quotient rule for limits. And then we have the sum difference rule. So on top here, I'm going to have the limit as x approaches 3 of 4x squared plus the limit as x approaches 3 of 2x minus the limit as x approaches 3 of 5. On the bottom, I'm going to have the limit as x approaches 3 of 7x plus the limit as x approaches 3 of 9. So both on the top and the bottom, I've used the sum and difference rule. Okay, I'm going to do 2 different things in the top here. For the first 2 limits, I'm going to use the constant multiple rule and pull out the 4 and the 2 in front of the limit. So I'm going to get, isn't this terrible? Right, we don't do this, except for when we're told to. So we're going to get 4 times the limit as x approaches 3 of x squared plus 2 times the limit as x approaches 3 of x minus, okay, limit of a constant is just the constant. So we're going to get 5 there. On the bottom, 7 times the limit as x approaches 3 of x plus 9. So if you want to label things, here we've used the constant multiple rule. And here we've used the constant rule. Same deal down here. Constant multiple rule, constant rule. We're almost done, but I think we can get there. I think we can just do it now. So we're going to get 4 times the limit is x approaches 3 of x squared. There's a rule for that. It's both. I don't know if this rule has a name. I feel like this rule has a name, but I don't know actually what it is. So I'm just gonna say we're using this rule here. We're getting 3 squared and then plus 2 times 3 minus 5 over 7 times 3 plus 9, which is literally the same thing I wrote up here. So it should be the same number, 37 divided by 30. So that's how you find a limit and express all the laws you had to use to do it. As you can see, it's nobody's cup of tea, probably, unless you are into masochism, I guess. Not fun. I don't like it, but it's important that we recognize that these rules exist because occasionally down the line, there's a time where we'll be doing a thing, especially with like some of the limit definition of the derivative stuff, and we're actually going to kind of appeal to some of these rules. Be like, oh yeah, remember we talked about like the product rule for limits? Well, right here we're actually going to break up the limit of this times this as the limit of the first thing times the limit of the second thing. And we're going to be like, yeah, we can do that because we talked about the limit less. So that's kind of why we're talking about. We still have a few more minutes here. Let's see. What else? Oh, I know what else I should talk about. I mean, there's so many things to talk about. Let's briefly, let's go that way. So here's a pretty common example of a limit. Limit as x approaches. Yeah, let's do that one. 0 times of x squared times, let's be unoriginal, sine of 1 over x. There's a pretty spiffy way of proving that this limit is equal to what it's equal to. But I don't really want to do it that way. Just because it takes a minute. But let me, let's actually back it up for a second. Sorry, I know I just said that one. Well, let's actually first talk about this one. The limit as x approaches 0 of just sine of 1 over x. So this limit does not exist. Here's one way you can see it does not exist. You can graph it. If you graph it, in fact, let me show you what it looks like. The graph looks ridiculous. The graph, I know we're almost out of time. I just want to show you real quick. Maybe not. So here's y equal to sine of 1 over x. Sure. And it doesn't look that crazy, but if you zoom in, it's just like a solid wall of craziness, right? Like, oh my gosh, it just back and forth, back and forth, back and forth forever, never, never, never. And the way people kind of argue this is that you can keep picking values of x that are closer and closer to 0, like x equal to, what's my choice here? I want to get 3 pi, So I want to get this, So I want, say, 2 over pi, or 2 over 3 pi. Let me ask you all a question. Are these numbers getting smaller or bigger? Well, let's see. If my numerator is getting bigger, my fraction is getting... I can't hear you guys. Bigger or smaller? Smaller. Be loud. Come on. Smaller. So these numbers are getting closer and closer to 0, right? Okay, but if you plug them in, 1 over 2 over pi is pi over 2. And sine of pi over 2 is 1. And 2 over 3 pi, 1 over that is 3 pi over 2. And sine of 3 pi over 2 is negative 1. And then if I plug this one in, it's sine of 5 pi over 2, which is positive 1. And then sine of 7 pi over 2, which is negative 1. Then positive 1, then negative 1. This function infinitely bounces back and forth between positive 1 and negative 1 as you get closer and closer to 0. Meaning the limit's never going to exist because you keep bouncing back and forth, oscillating back and forth between negative 1 and 1. So this limit does not exist. This limit does. And the way we can show this is by what's called the squeeze or sandwich theorem. So it's certainly true, and this is how we often deal with squeeze theorem limits for sine or cosine. It is true that sine of anything is always less than or equal to 1, is always bigger than or equal to negative 1. Doesn't matter what's in the argument there. In this case, it's 1 over x. So we multiply the whole thing, the whole inequality by x squared, which is always non-negative, so we don't have to worry about changing the direction of any inequalities. And multiply by x squared, we get negative x squared is less than or equal to x squared times sine of 1 over x is less than or equal to positive x squared. Cool. If we look at the limit as x approaches 0 of negative x squared, what do we get? Negative 0 squared, which is 0. How about the other side? If we look at the limit as x approaches 0 of positive x squared, what do we get? Also 0. So the limit of that's 0, the limit of that's 0, the limit of that's between 0 and 0. It's gotta be zero. So what we're really saying here is you take the limit of each part, the inequality still holds. And I know we're out of time, but I just want to show you the picture because I think it's really worthwhile. That's zero, that's zero. If you're bigger than or equal to zero and less than or equal to zero, you have to be zero. There's no other choice. Graphically, here's how things look. Let's go back to that. So here's y equal to x squared. There's y equal to negative x squared. And here's x squared times sine of 1 over x. And if we zoom in a bit, you can see, oh, look, my function is stuck. It's stuck between negative x squared and positive x squared, and it just keeps bouncing back and forth, back and forth, back and forth, getting closer and closer and closer to the values it's getting squeezed to by these two things that are both getting closer and closer to a y value of zero. So that's kind of a prime example of the squeeze theorem or the sandwich theorem. I'm out of time, so stop talking.